All right, as we continue our discussion here in Chapter 10, we're looking in Section 10.4, using inscribed angles and polygons. And so again, we're going to continue our discussion involving circles. So first of all, some vocabulary. An inscribed angle is an angle whose vertex is on a circle and whose sides contain chords of the circle. In other words, an inscribed angle is something that looks like this. Okay, so this angle here is inscribed because, again, if you look at the two sides of the angle, the two green sides, those are obviously chords of the circle, and the vertex lies directly on the circle. So that is what we call an inscribed angle. Okay, and then an intercepted arc is the arc that lies in the interior of an inscribed angle. The endpoints of the angle are the intersected arcs. So in other words, if I draw an inscribed angle, again, something like this, well, then the intercepted arc is that blue arc right there. Okay, it just goes from the endpoints of the circle. So, or the endpoints of the angle, I should say. So, again, that's what we're looking at when we talk about intercepted arcs. Okay, an inscribed polygon now. With an inscribed polygon, that's just a polygon where all the vertices lie on the circle. So if I draw an inscribed triangle, all the angles or all the vertices lie on the circle, and we would call that thing an inscribed polygon. All right. A circumscribed circle is a circle that contains the vertices of an inscribed polygon. Okay, so again, a circumscribed circle is a circle that contains the vertices of an inscribed polygon. So, in other words, if you look back up here, we say that the triangle is inscribed in the circle, or we can say that the circle is circumscribed by the triangle. So again, it's just it's two different ways of saying really the same exact thing. Okay. All right. So as we get rolling here. The first theorem we're looking at today says how to find the measure of an inscribed angle. Okay, and this is not quite as simple as the measure of a central angle, right? Because recall, if I draw in the central angles ACB, well then the measure of the central angle is the same as the measure of the arc. Okay, now when we're talking about inscribed angles, to find the measure of the inscribed angle, you take half of the measure of the intercepted arc. Okay, so it's going to be 1/2 arc AB. Okay, and so that's kind of what we're looking at there. Do note too that you could also say it's 1/2 times the measure of angle ACB, the central angle, because again, we know this arc and this angle have the same exact measure. All right, so the inscribed angle, angle D, is 1/2 of either one of those two things. So just some quick examples here. The first one says find the indicated measure in circle P. All right, so we got to find the measure of angle S. Well, there's angle S right there. We know that the arc, it's an inscribed angle, right, because the vertex lies on the circle. And so we know that it's half of the intercepted arc, so S is equal to 1/2 times 60. So the measure of angle S is just 30 degrees. Part B says find the measure of arc RQ. All right, so here's arc. Let me go ahead and erase this diagram just a little bit so we can clean it up and see what we're looking at here. Find the measure of arc RQ. Here's RQ. All right. All right, so what we're looking at here is it's really a two-step process now. Okay, first of all, if I know that this angle here is 37, then I know how to find the arc measure. Just take it and multiply it by 2, so I know this arc measure has to be 74 degrees. Okay. The second thing you have to recognize is that since RS is a diameter, and we know that because it goes through the center, then we know that this whole arc, SQR, is a semicircle, which is 180. So I know to find RQ now, I have to do 180 minus 74. Okay, so RQ is 180 minus 74, which is 106 degrees. Example 2 says find the measure of arc HJ and angle HGJ. what do you notice about HGJ and HFJ? Okay, so again, this is a more complicated diagram, but here's essentially what you're looking at. You notice, and my encouragement to you would be, as soon as you get a diagram, mark everything you know. So as soon as I know that this angle is 39, I can find this arc. 2 times 39 is 78 degrees. Okay, and now what you're looking at is, now you say, all right, well, hold on a second. Now if I look at this inscribed angle, you'll notice that that angle intercepts this arc, and you'll notice that arc is 78 degrees. So to go from the arc to this angle, cut it in half. So the measure, well, first of all, arc HJ is equal to 78 degrees. And so now we can say HGJ, the measure of angle HGJ, well, it's 1/2 of the 78, which is 39 degrees. And it says, what do you notice about angle HGJ and HFJ? So HGJ and HFJ. And the thing that you notice is that they're the same. They're both 39 degrees. All right? And it should make sense because they both, if you look at the two angles, they both intercept the same arc. Okay, they both intercept arc HJ. And so that's exactly what we're looking at here. It says if two inscribed angles of a circle intercept the same arc, then the angles are congruent. So given this diagram, you'll notice that angle ACB and angle ADB intercept this same arc. If they intercept the same arc, that means that they have to be congruent. So ADB is congruent to ACB. All right, so example 3 says name 2 pairs of congruent angles in the figure. Well, again, there's a lot of crossing lines here, so it's hard to pick out, but if I have the luxury here of tracing it with colors, so you'll notice that that angle and this angle both intercept the same arc. All right, so as a result, we know that angle, well, let's see here, SPR. All right, so this angle is congruent to that angle, SQR. There's one set, and then now we got to find another set. So again, I have the luxury here of erasing and looking at the diagram again. So you'll notice that this angle and this angle also intercept the same arc. They both intercept arc QP. Therefore, they must be congruent. So the other one that you know is that angle, let's see here, PSQ is congruent to angle PRQ. Again, they intercept the same arc, so they must be congruent. All right, find the indicated measure here. So now we're kind of looking at some different ideas. So measure of angle GHJ. GHJ is this angle. Well, since I know that that arc is 100 degrees, I know the measure of the angle is 1/2 of 100. So the arc measure is 50 degrees. Okay. Find the measure of arc CD. All right, now we're just going the other way. I know this angle is 40. It's an inscribed angle. To go from the inscribed angle to the arc, double it. So the measure of arc CD is just 80 degrees. Measure of angle RTS, okay, RTS, you'll notice that angle RQS and RTS both intercept this arc. Therefore, these angles must be congruent. So the measure of angle RTS must be the same as the other angle, which is 31 degrees. All right, so again, just kind of applying these different ideas that we're looking at. Okay. The next theorem we're going to look at, it says if a right triangle is inscribed in a circle, then the hypotenuse is a diameter of the circle. Okay. Conversely, if one side of an inscribed triangle is a diameter, then the triangle is a right triangle. Okay. First of all, let's understand how we know this. Okay, we know this because if this is my inscribed angle, then the arc that is intercepted is this arc here. Well, that arc there, since AC is a diameter, happens to have a measure of 180 degrees. Right? And so remember to go from the arc to the inscribed angle, cut it in half, so we know that's got to be a right angle. That's where this theorem comes from. Okay, that's why this works. So it says the measure of angle ABC is equal to 90 if and only if AC is a diameter of the circle. So again, if you have a triangle inscribed in a circle and one of the legs is a diameter, then that means it's actually the hypotenuse, which makes it a right triangle. The other one says a quadrilateral can be inscribed in a circle if and only if opposite angles are supplementary. Okay, so if and only if D and F and E and G add up to 180 degrees. Okay, understand again why this works. We don't know how big this angle is, but we know that that angle there intercepts arc FGD. Okay, and then conversely, we know that angle, let me trace this with a color, FG, so opposite angles, right? We know that this opposite angle intercepts arc FED, and you'll notice the two arcs that are intercepted, FED and arc FGD, make up the whole circle. Well, the whole circle is 360. Okay, so now when we're talking about angles, well, if the whole thing is 360, then that means that this angle and this angle, since they're inscribed, has to be half of that, which is 180. So that's where this theorem of inscribed. All right, so the first example here says find the value of each variable. So I know that opposite angles have to add up to 180. So y is equal to 80 degrees. I'm just doing that in my head. And I know that these two angles add up to 180 as well. So x equals 180 minus 88. 180 minus 88 is 92 degrees. Okay, so your two, y is 80, x is 92. And again, this is parts B and C are the same, so I'm going to go ahead and let you guys kind of roll. I'll do part B with you. Part C you can do on your own. So again, in this particular diagram in part B, 8x and 4x have to add up to 180. And then we also know that 3y and 3y also have to add up to 180. Okay, so you'll see 6y is 180, so y equals 30. And then in this particular example, 12x equals 180. Divide by 12, so x equals 180 divided by 12 is going to be 15, I believe. Let's see here, 165. Yep. Okay. And then part C again is there for you. All right. So again, that kind of sums up section 10.4, inscribed angles and how they relate to arc measure, and then also just a few different theorems about inscribed polygons in triangles. So any questions you have, as always, bring them to class, and we'll go from there.